This lesson covers how to build a root locus using rlocus or rltool in Matlab. So the root locus is the path taken by the closed loop poles as they migrate from the open loop poles to the open loop zeros as k root locus varies from 0 to infinity. So I've got the gain right here, KRL, shown up here in the forward loop, but it could also be in the feedback loop. But we'll keep it here in the forward loop for now, and then you're given G and H come from your system dynamics. So the open loop transfer function is KRL times GH, and I'll make a point here that Matlab is going to move KRL for us. So our input to Matlab will be an open loop transfer function, but without the K. It'll just be G and H. But the closed loop transfer function is formed, and here's the denominators of these two guys. Those are the characteristic equations that Matlab solves for and plots the locus of roots on the S-plane. So let's do that. Let's build G. G equals TF 1 1 1 4 5. There's G, and H for this example, TF 10 1 10. There's H. So our open loop transfer function, again, does not include the K, is series of G and H. Okay, let's type help on rlocus. Help rlocus. So it computes and plots the root locus of the single input, single output, linear time invariant model sys. Here it's got sys in the forward loop, it's got their K in the feedback loop, but we already talked about it doesn't matter, it's the same open loop transfer function. And so the feedback gain K varies from 0 to infinity. So let's plot what we have, our locus of our open loop transfer function without the K, and see what happens. Alright, there's the root locus. So it's got the location of the open loop poles and the open loop 0, and then it shows how those poles, as you close the loop and vary gain K from 0 to infinity, what happens. So anytime I click on a point here, this point is a closed, even though the system input for our locus is the open loop transfer function, that point that I click on is a closed loop pole corresponding to KRL equal to 6.2, and it gives the damping ratio and the natural frequency of that closed loop pole. I can click over here, same thing, it gives the gain, the KRL equals 0.573 to put the closed loop pole at this location. We can also, let me move these guys, we can also add a grid. So there's the grid. This shows lines of constant damping ratio and contours of natural frequency. So here's one that says 0.64. I guess if I click on here, it should be a damping ratio of 0.64, and it is. And the gain to put it there is 7.02. Again, clicking on that point, that is a closed loop pole when the gain is 7.01. The other command is rltool, and put the same open loop transfer function and see what that does. Okay, so that opens syso design for syso design task, a toolbox kind of thing. This has a little bit more power. You can start to add more complex controllers, and we'll get to that later on. But it has the same root locus that we saw before. It has these pink boxes, and they default to the KRL value of 1. That's where the boxes default to. And then you can click on the box and start moving it, and it will show you how the poles move. So there's the current location, and then if you let go, it will show you that what the loop gain was to get it there, 1.31. Click over here, same thing, we can move that guy up. It's going to show the damping ratio and natural frequencies, how they change as we move the closed loop poles around. And then you got to let go to see what the loop gain, or the KRL 3.27 was to get you there. Again, you can add the grid if that helps, and you can see here we want to move to say 0.74 on the damping ratio. let go, and it shows the gain KRL to get you there was 4.45.